So we are going to go over decimals. You guys ready? So a little bit of history and review of decimals. So decimals used to be called decimal fractions. And they have not been around for very long. They were only introduced a couple hundred years ago. I believe it was by a German army guy who thought it would be easier if we only worked with fractions that had only 10 in the denominator. So he said we should only work with fractions like 1/10 and 1/100th because he thought it was much more efficient. And you know how those Germans are about efficiency. Most of them are pretty good. So, and if we're only going to work on base 10 fractions, he said, then we can just ignore the denominator and know that when we write something like 1, 1, 1, 1, so those are those 4 ones. And suppose I had, right before the tenths would be our oneths or ones. Either way you say it, it doesn't really make much difference. What he did to distinguish the whole numbers from the decimal numbers was to circle the ones place. So where we would write a number like 3.14, he would write it as 3 circled 1, 4. And then you were just to look at that and know those were 3 ones, 1/10, and 4 hundredths. And how many people like decimals over fractions here? Most of you? Okay, so his idea did not take off. People they weren't excited about it. They thought it was kind of ridiculous. We have all these other fractions. Why would we give all those up, like a half and a third and a fourth? And he had all kinds of reasons why it was more efficient. And he was right, because that's what people like about decimals right now. It's a lot easier to deal with. So more into why he did that. Well, it just goes on, the way our number system is structured right now. We have our let's say our thousands. We have our hundreds. So he was just extending things in the other direction. Our tens, our ones, our tenths, hundredths, and I don't quite have room. I wanted to get the thousandths. So we'll just squeeze those suckers right there. But do you see the symmetry around the ones place? On one side is the tens, the other side is the tenths, right? Tens on this side, 1 over tens on that side. 1 is in the middle. Make a nice big fancy 1. On one side I have 100. 2 places to the left of the ones, 2 places to right are the 1 over 100ths. Similarly, our thousandths and 1 over 1000ths. So the symmetry really is around the ones. I can't remember who decided to put the decimal point in there, but does everybody use a decimal place in the world? The answer is no. Some cultures use a comma between the ones and the tenths instead of a decimal place. And then they come to our country and see commas all over the place and they freak out. That doesn't make any sense. There's only one place to split the whole numbers and the fractions. Okay. So in some sense, his idea of identifying the ones as the separator is a good idea, given the balance of the tens versus the tenths. We also use sometimes exponential notation. So hundreds would be 10 to what power? The second power, right? Thousands would be 10 to the third. Tens would then be 10 to the 1. The ones are 10 to the 0. It would be actually 0, yeah. Yeah. That is correct, yeah, because negative exponent means flip the base. So that means 10 to the negative 1 is 1 over 10 to the 1, and 10 to the 1 is same as 10. What would hundredths be then? Correct, 10 to the negative 2, and then thousandths is 10 to the negative 3. And I think the exponential notation really makes that stand out, that one's living in the center. Okay. With scientific notation, right, the negative exponent means move the decimal place to the left, right? So we'll cover scientific notation later, but since you brought it up, yeah, so if we had something like 3.14 times 10 to the negative second power, we would rewrite that by moving this decimal point 2 places to the left. So moving it past the 3 is one place, and then one more place. I would have to fill a 0 in there. I like to write a 0 in front. So it'd be 0.0. So the decimal point moved from here 1, 2 places to there. Okay, so we'll play with scientific notation later. Negative exponent, if the base is a whole number, means we're dealing with a fraction, because that would really be 1 over 10 squared. 1 over 10 squared is 1 over 100. And so essentially we would be taking that 3.14 and dividing it by 100, which should make the number smaller when we're done dividing. Okay, so that's scientific notation. We'll look at that again later, but yes, so the idea of decimals, the idea of negative exponents is super important to scientific notation. All right, now I got to get one of my online toys. Oh, what did I just do? Whoa. Let's bring you over here. I want online base 10 blocks. And these I think are good. Nope. So let's see. Oh, this one doesn't let me switch to. I'll have to come back to this later. I have one that lets me switch to decimals. Whoa, interesting. It's not this one. Give it one more try. Oh, I bet it's in this one here. Base 10 block decimals. Let's see, where do I grant it permission? I don't see it. Java needs your permission to run. Why won't you just run up here? Okay. Allow. Later. Come on, you can do it. Allow. I'm allowing. I have to reload it. Oh, here it goes. Okay. So here we have some control. We can play around with the problems. This one's an addition one. You can do others that are just playing with blocks. But I can make the decimal place 2 places. So then I can show my ones, tenths, hundredths if I wanted to, and then they're giving me a problem to do. So I'll put a link to this site, but it's the National Online Manipulative Library. And so just about any skill that you want to play with, they have an online manipulative for it. And they're organized in a variety of different ways. You can find things by topic, by grade level, and there's just tons of online toys here for doing math. You could spend weeks here. So Morgan, if you guys are bored on your honeymoon, you can come here and play, warming up for next year. Oh, bummer. Okay. That's okay. We had to wait a few years for our honeymoon when we got married. So again, those online toys are nice, especially if you don't have the physical toys. We have the physical toys here in front of us, and so we'll play with those later. I will post a link to the online manipulators library and to the specific ones I like, so you don't have to search through them. Okay, so let's play a little more. So again, we're just dealing with fractions again, and we got really good at fractions before. And so we'll play around with the operations in just a minute, but just some more on decimals. Decimals related to fractions. So a lot of times I look at that number right there and I would say 3.14, but that's slang. And it's okay to use that slang. We all use slang a lot. The proper way to read that would be 3 and 14 hundredths. And in order to read a decimal properly, you have to be able to identify each place value, in particular, the last place value you see. But this is the hundredths place here. Now that makes me think of a mixed number. This is essentially a mixed number here. So I could just write it out in fraction notation, 3 and 14 hundredths. So anytime we need to change a decimal to a fraction, all we have to do is read it properly. Anybody compelled to do anything else to this particular fraction, mixed number? No? Maybe? We're done? Reduce, maybe. We might reduce. Yeah, sometimes we like to reduce. So we could say, oh yeah, 2 goes into the top 7 times, 2 goes into the bottom 50 times, 7 goes into 49, but not 50, so I can't really do anything else. So I could put it in a reduced form. So 3 and 7/15 is the same thing as 3 and 14 hundredths, which we normally write like that. So when you're dealing with decimals with kids, try as hard as you can to avoid the slang, even though it will creep in often because you're used to it. Because again, we want to get the kids used to the place value, because if they don't master place value, then decimals are worthless. We've got to nail those places down, which means they have to know the places on the other side well, because the decimals just take them the other direction. Right? Thousandths, after thousandths on the left, what do we have? So then on the right, after thousandths, what would we have? Did I say that wrong? Thousands on the left, thousandths on the right. 10 thousandths on the left, 10 thousandths on the right. So every place on the left has a matching place on the right. Okay, so if they don't have the left side places mastered, then they're going to struggle with the decimal places. So we got to nail those. So changing a fraction to a decimal to a fraction is easy. All we have to do is be able to name place value. What about going the other way? Oops. Fraction to decimal. Okay, let's pick one of my favorite fractions, 1/4. Now we've seen 1/4 a lot. Does anybody remember off the top of their head what 1/4 is as a decimal? 0.25. Okay, and again, that's slang. What's that really mean? 25 hundredths, which we could write, just like you said it, as 0.25. Now, if I'm messy, that I might not notice that as a point right there. So sometimes on paper, I'll enlarge my point to be clear. But still, some people are really messy and they'll look back at that. Let's see, is that a 25 or is that a 25 hundredths? So I'm in the habit of putting a 0 in front to be clear about it. And I'd highly recommend doing that with kids also. No ones, 2/10, 5 hundredths. Okay, so we are used to that, but how would we show somebody that that's true? Almost divide 4 into 1. Yeah, so this is 1 divided by 4. We could use the goes into symbol. So we want to see how many times 4 goes into 1. Now we know 4 goes into 1 0 times. So what we do is we put the decimal place here and then fill in some zeros. And the thing about, we never know how many zeros to put unless we have experience with this. The key is, as long as the denominator is a whole number. So just make a little note. Denominator, it's supposed to be an R, must be a whole number. As long as the denominator is a whole number, we can proceed and know that the decimal and the answer goes in the same spot. Okay. And the main reason is just the way our division algorithm works. If the denominator is a fraction, then you have to think about things totally different. Remember how we did the groups of with fractions? That was very challenging. We all struggled with that. If it's a whole number, it's easy. If it's a fractional denominator, it's much harder to think about. And without toys in front of you, it's like impossible to think about unless you practice it a lot. So super important. Denominator must be a whole number. Otherwise, this is very, very, very difficult. So I'm just going to do it right away. 4 goes in. So once I know where the decimal point goes in the answer, I can just divide until I'm done. 4 goes into 1 0 times. So then I move on. Next 2 places give me 10. How many times does 4 go into 10? 2 times. Carry out your division. 2 times 4 is 8. Make sure you line up place values. Subtracting 10 minus 8 is 2. Now that should be smaller than my divisor, which is good. So I bring down the next digit. 4 goes into 20. 5 times. 5 times 4 is 20. I get a 0 remainder, so I'm done. Okay, so we can justify it. So to change a fraction to a decimal, you just have to carry out division. You have to locate the decimal and the answer. And then you have to add zeros as necessary to the dividend. So we're modifying the long division algorithm to help us do decimals. Okay. So again, that's an algorithm to convert a fraction to a decimal. Does it always work easy? Yes and no. Sometimes. Let's try it on a different one. So let's try 1/3 as a decimal. So let's see, that means I have to take 3 into 1. I know it's 1 point, and then I'm going to put a 0, and we'll just keep adding zeros as we need it. Is my divisor a whole number? Yes. 3 goes into 1 no times. 3 goes into 10 3 times. 3 times 3 is 9. Subtracting, I get a 1. Yeah, so I put another 0. Yeah, and the question is, when do I know it repeats? And the key on when I know it repeats is if the remainder repeats. So we're not looking for a repeat in the top. We're looking for a repeat in the remainder. This is super important. We're looking for a repeating remainder. Once we find, and I'll explain why in a little bit after we do a couple of examples, but once we find that repeating remainder, then we go, I gotcha. I know your pattern now. But just just looking at the answer isn't enough. So again, I bring, and I'm kind of guessing, I think I have a repeat here. I started with a 1 there and I have a 1 here, right? But I'm just going to do it one more time to be careful. So I bring down that 0, 3 goes into 10 3 times. 3 times 3 is 9. Subtract, boom, there's my repeating 1 for sure. Okay. And so now I know I do have a repeat. So the repeating part is that 3 for an ever and ever and ever. And so usually we do is we put a bar over the repeating part. Now technically there's really no difference between 0.33 with a bar over both 3's or 0.33 with a bar over the second one or 0.3 with a bar over just 1 3. I prefer the one with the least ink, which is this last one, but they all lead to the same answer. All you need is enough to show the pattern, and the pattern is a single 3, so I only need to bar over a single number. Is it wrong to write this first one right here? No, because what that tells me is to start with 0.33 and then put another 3 3 and another 3 3 and another 3 3 forever and ever and ever, right? It's the same end result, right? But usually we go with the one that's less ink, okay? All right, so let's try another one. How about 1/6? So that means 6 goes into 1. Put the decimal point in the dividend and the answer. 6 goes into 1 no times. 6 goes into 10 once. 1 times 6 is 6. I'm careful lining up. What do you do if kids have trouble lining stuff up? You could draw lines, give them graph paper, I think is the easiest thing. Have them do it on graph paper. There's lines already there to help do that division. Subtract, I get a 4. Bring down the 0. What, 6 times? 6 times 6 is 36. Subtract, I get a 4. And at this point, bells should be sounding because I just found my repeat. There's 4, there's 4. So the repeat goes with the 6, not the 1. Right? If you're not sure, do it again. So let's continue doing it again just to double check. I have a 4 remainder. I put a 0 here. I bring that 0 down. 6 goes into 40. 36 is the closest I can get. 6 times 6 is 36. Subtract, and there's my 4 again. So it's only the 6 that repeats here. So I would say 1/6 is equal to 0.16 with a bar only over the 6. Okay. How you doing, Maggie? Having fun? All right, let's do a couple more examples and then that'll be enough for today. Let's suppose I had 1/9. What does that equal? Yeah, 0.1 repeating. 1 1 1 1 1 1 1. Well, you wouldn't really call it 1/10 repeating because the next spot would be 100th and then 1000th and so on. Yes, that is slang. But it sounds, okay, I'm gonna have to think about that. So Maggie said, can we call it 1/10 repeating? And the 10th only refers to this particular place. Because here the 1 is repeating and now it's in the hundredths place. So it's, oh boy. I don't know how to resolve this issue right now. I will have to think on it. Okay, so can we call this, I'll have to convene the math department to talk about this. 1/10 repeating. It feels odd to say that. Big question. Ask math department. Okay, I'll send this to them after. Let's take a look at 2/9. So 9 goes into 2 how many times? Oh. 20, it goes in 2 times. Holy shit. 18, subtract, there's another 2, and it's just going to repeat that pattern. Okay, so this is one of the cutest patterns ever in mathematics. Guess what 3/9 is going to be? This is 3 repeating, and 4/9 is going to be 0.4 repeating. 5/9 equals, oop, I forgot to put the repeat. Yeah, isn't this a beautiful pattern? 5 repeating 6/9 is 0.6 repeating. By the way, 3/9 can be reduced to 1/3, right? And 6/9 can be reduced to 2/3. And think about it, 1/3 plus 1/3 is 2/3, right? And so if I have a bunch of 0.33333s and I add that to another 0.33333s, shouldn't I get 0.66666s? Not cute? It is. Now this gets even better. Check this out. This always blows my mind. Suppose I took, let's pick on 4/5, or 4/9, sorry, and 5/9. 4/9 is 0.44444 forever and ever and ever, right? And 0.5, or 5/9 is 0.55555 forever and ever and ever, correct? Now, remember, what's the key to fractions? With fractions, we can add fractions if we have the same denominator, right? Well, decimals, denominators are designed to be the same. So wouldn't you agree that these guys right here have the same denominator because they're both tenths? And these guys are both hundredths, thousandths, 10,000ths, and so on. So I can just add them up because they already have the same denominator. How many ones do I have here? No ones. How many tenths do I have altogether? 9/10. How many hundredths do I have? How many thousandths? 10 thousandths? 100 thousandths? I'm going to have nines forever and ever and ever. What do I get on the other side? What's 4/9 plus 5/9? 9/9 or 1, but it's also 1. Now this is something to think about and maybe dream over, that 1 is the same as 0.9 repeating forever. No, I'm not talking, we have done no rounding here. Not yet. We'll talk about rounding next time. We haven't even got to rounding. We haven't gotten to rounding yet. Forget about rounding. But yes, okay, that's interesting. Ooh, crap, what do they do? No idea. Excited. 0.9 repeating, we claim is 1, just like we claim that 1/3 is equal to 0.3 repeating, or 1/4 is 0.4 repeating. That kind of weird? It's kind of weird. Okay. But do you like 1/3 is 0.33333333? You like that? Okay. It's a direct consequence of that. Yeah, I know. It takes some getting used to. We'll talk about that. We had some weird things last quarter too. We'll always have weird things in math. All right, so this video has gone on long enough. I want to stop it here. I need to talk more about in the future patterns from fraction to decimal. Sometimes fractions terminate, like 1/4 is 0.25, boom, done. But sometimes fractions go on forever. Can we identify ahead of time by looking if a fraction will terminate or repeat forever? Turns out we can. So that you guys could just make up a fraction. Somebody make up a fraction for me. 3/7, that repeats forever. It does. I can tell by looking. I'll tell you next time how. 7 doesn't go into 3? Nope. No, for example, 1/125, that terminates. 3 over 64, that terminates. But this guy repeats forever. And it turns out there's a way to tell just by looking with just the information we learned last quarter. So we'll go over that next time. I'm gonna leave you hanging there. It's like, you know, at the end of those TV episodes, there's this, oh, something happens at the end and you can't wait till next time. I'm hoping I get you on the edge of your seats. Until Wednesday.